We'll have a walkthrough of this paper. This paper is titled Optimized Ensemble Learning Approach with Explainable AI for Improved Heart Disease Prediction. This paper is authored by these two authors, if I pronounce correctly, Ibomoiye, Domor, Mienye and Nobert, Jere. So what I'll try to do is I'll try to highlight the keywords while doing the walkthrough. So basically it's using ensemble approach and explainable AI approach. Okay, and the problem statement is heart disease prediction. So you'll be using ensemble learning algorithms, Bayesian optimization, which will be used for hyperparameter tuning, and Shapley additive explanation SHAP for interpretability. So under ensemble you will be doing adaptive boosting, random forest, extreme gradient boosting, and the data sets they used were of Cleveland and Framingham. They got a good results for the performance metric specificity and sensitivity as 0.971, 0.989, 0.921 and 0.975 for the two data sets. So machine learning models are considered as black boxes because they don't have interpretability and transparency aspects. So when they don't have that, their decision making is not understandable by humans. Hence explainable AI, and one technique of explainable AI called SHAP in this paper will be achieving that interpretability and transparency. SHAP is game theory based. It is used to explain the outputs of machine learning model, features of machine learning model. So in this paper, SHAP will be giving insights about the features which will be influencing the model's prediction. So we have something called as SHAP values, which are nothing but SHAP features. So with this understanding of these features, exploring these features, it will be easier for us to get why ML has given whatever the results it has given. So these are literature contents, and the referred papers will be having different kinds of algorithms and authors. Say CART is being mentioned here. Then hyperparameter optimization strategies are mentioned here. SHAP for interpretability is mentioned here. Now coming to the data sets, there are two data sets. One is Cleveland heart disease having around 14 attributes and so on and so forth. So the other one is Framingham heart study data set. So around 5209 persons aged 30 to 60 years and so on and so forth. So what the data sets consist of is all the parameters like age, sex, smoking status, blood pressure, cholesterol. Let us directly look at the tables for few of the features mentioned. For example, you can see here Cleveland heart disease data set, and there are 14 features you can find out. Let us say one feature is age, the other feature is sex, let us say one feature is THAL, which is for thalassemia. One feature is CA, so this is for major vessels colored by fluoroscopy. CP is for chest pain type, COL is for cholesterol, say FBS is for fasting blood sugar, Framingham Heart Study data set, you can see here 16 features. I will just take few of them. Say for example, current smoker, yes or no. Cigarettes per day, how many? And diabetes, yes or no. BMI, what are the heart rate, glucose. So all these are the features, and these are the two data sets taken. And these are the two data sets taken. Now coming to random forest, it is an ensemble algorithm, right? So what random forest will be doing, it will be creating multiple decision trees. So what it does is, it will be combining several decision trees. So say for example, we have a data set, and there are n instances and m attributes. So what the random forest will be doing is, it will be building each tree by selecting a random subset of instances and a random subset of attributes at each node to split on. So remember here the keyword being mentioned is split on. So because of this randomness, you get diverse trees. So for every new instance, so the tree in the forest votes for the instance to belong to the most frequent class. So prediction is given by this y cap, and it is represented as mode of y1, y2, yt, where t is the number of trees in the forest. y1, y2, y3 are the prediction at that particular position. Now say for example, you have XGBoost. Okay, it is gradient boosting algorithm, and it is an improvement, rather it's an improvement over a gradient boost. Okay, what it does is, it will be iteratively refining the predictions through an ensemble of decision trees. Okay, every new tree, what it will try to do is, it will correct the errors made by the previous build tree. Now again, y cap I, for an instance I, after t rounds of boosting is given by this ft of xi. So where ft is teeth tree's contribution, xi is the feature vector at the ith instant. The objective function for XGBoost is given as L of y I comma y I cap plus summation of omega ft. Here L is a convex loss function. What it does is, it finds the difference between predicted y cap and the actual y at the ith instance. Omega is the regularization term. So it penalizes the complexity of the model, including the number of leaves, magnitude of leaf weights, entry ft. So what it tries to do is, it tries to do overfitting, or to prevent overfitting rather. So XGBoost for optimal performance needs to fine tune its parameters. The parameters can be learning rate, depth of the tree, and so on. Now for that, it may take the help of Bayesian optimization also. So what Bayesian optimization does is, it will be searching the hyperparameter space, consider the past evaluation results, and find the set of best hyperparameters that minimize the validation error. So we referred among the ensemble random forest, then XGBoost, then the next one is AdaBoost. So it will be combining multiple weak learners. So it will be having a sequence of weak learners, and they'll be repeatedly modified versions of the data. The predictions of all of them are combined through a weighted majority vote to produce the final prediction. What is the output of AdaBoost algorithm? It's a weighted sum of the weak classifiers, and it is given like this: sine of t equal to 1 to t alpha t htx, where t is the total number of weak classifiers, ht of x is the prediction of the teeth classifier, and alpha t is the weight of the teeth classifier. This is based on the error rate. The error rate of each classifier is given using this formula, where wi is the weight of the ith instance, yi is the actual label, and I is an indicator function that will be returning 1 when yi is not equal to ht of xi and 0 otherwise. Coming to Shapley, Shapley additive explanations, they are also called as SHAP values. They explain the predictions. They explain the predictions of an instance by computing the contribution of each feature to the difference between current prediction and the average prediction across all instances. So basically we remember that SHAP, what it will be doing is interpretability it will be doing, and it will let us understand the ML outcomes, ML predictions in a better way. Okay. So in this paper it will help us in understanding the outcome of ensemble classifiers, be it random forest, XGBoost, AdaBoost. Okay. So SHAP is actually game theory based, cooperative game theory based, and here it will be allocating payout to players based on their contribution to the total payout. Now when you do that in machine learning, the players are nothing but the features here, and the payout is nothing but the prediction output of the model. So Shapley value for say feature I, it can be calculated using this phi I formula, where you can see the terms S is there, F is there, F of X is there, F of X of S is there. So F is the set of all features, S is the subset of features, but it will be excluding I. This is the cardinality of S, this is the cardinality of F. F of X of S, it is the prediction when only the features in the set S are used, and F of X, S union I is the prediction when the features in S along with feature I are used. Now the sharp value phi I actually represents average marginal contribution of feature I over all possible combinations of features. Now, what they have done in this paper is they have come out with a herd disease prediction using ensemble approach. So what they did is, as usual, typical machine learning approach is dividing the data set into training and testing, and they had created a hyper parameter space for each classifier. They use Bayesian optimization, and so that you will get optimal hyperparameters that will be maximizing the area under ROC curve. So this is called as AUC. So in this paper they use 5-fold cross validation method, okay, for the training data set, so that rigorous evaluation of hyperparameter sets happens. So 5-fold cross validation means training data set is divided into 5 smaller subsets, and for each set of hyperparameters tested, the model is trained on 4 of these folds and validated on the remaining one. This procedure is rotated so that each fold serves as the validation data once. So this is the algorithm for that. You have the data set D, and the output of this will be prediction and explanation of the herd disease diagnosis. It will be using ensemble models. You will be dividing your data into training and testing set. So you have H hyperparameter space. You have defined the objective function. The purpose of the objective function is to maximize the cross-validated AUC. So for each model you will be applying the Bayesian optimization. Now then you will be getting what basically you are doing is you are training and evaluating the model M. Then you will be selecting the best model called as M best. And what is M best? With the highest AUC. So explainable model will be, input will be M best and D test. So sharp values will be calculated on the predictions. The sharp values will be plotted, and M best is nothing but the optimized ensemble model, and this will be the final component will be the explainable model of that. The performance evaluation metrics are as usual. First one is accuracy. They are taken. What it does is it measures the proportion of true results, means true positive and true negatives. Then sensitivity. Sensitivity, the other name for sensitivity is recall. It measures the proportion of actual positives currently identified in the model. Okay, and specificity, it is also known as true negative rate. It measures the proportion of actual negatives currently identified, and it is crucial for ensuring that the model is not overly sensitive to positives. Then you have F1 score. It's a harmonic mean of precision and sensitivity. These are the formulas. Accuracy is true positive plus true negative divided by true positive plus false negative plus true negative. Recall is true positive divided by true positive plus false negative. Specificity is true negative divided by true negative plus false positive. Then F1 score is 2 into precision multiplied by sensitivity divided by precision plus sensitivity. So ultimately you will be calculating precision as this TP divided TP plus FP. As you can see here, uh, if you can see this table, the optimal parameters for Cleveland data sets you can get. Okay, so you have the classifiers as random forest, XGBoost, ADA boost, and these are the optimal values for the hyperparameters. Similarly, they have given for hyperparameters optimal values for Fermigan dataset also. Then you can see the performance on the Cleveland dataset. Optimized XGBoost and optimized ADA boost is showing the performance measures 0.984, 0.97, 0.989, 0.985. Same is the case with Framingham dataset also. Now once this was done, you can see here SHAP values. We'll see directly the SHAP mean absolute SHAP values, and you can see here CA is having the highest impact on the hard disk prediction, followed by CP and SEX and Tharand, and the least will be kind of FBS or TRES BPS and so on. Okay, so what CA stands for? Number of major vessels colored by fluoroscopy. THAL stands for thalassemia. CP stands for chest pain type, and SEX stands for sex, male or female. So FBS is fasting blood sugar, it doesn't have much impact, is it not? So same is the case visible here. You can see highest values of CA, then followed by CP, THAL and SEX and so on. If you look at the mean absolute SHAP values for the Birmingham data set, so they have the average impact on model output magnitude. You can see age and cis BP followed by cigarettes per day are the affecting factors. Even here also it is same is visible in this plot. Age, cis BP and cigarettes per day followed by BM and so on. Rather diabetes or previous strokes, all those aspects are not having the impact, that much of the impact. And there is a comparison table here. This is the optimized XGBoost proposed by the authors of this paper, which is having this much performance, and they have compared that with other researchers. And you can see here many of the papers have not used explainable AI component. Here rather it is used. So this was a short discussion of the paper, and this paper actually is authored by these two gentlemen, Ibomoiye, Domor, Mienye and Nobert, Jere, and the title of the paper is Optimize Ensemble Learning Approach with Explainable AI for Improved Heart Disease Prediction. The objective is for learning purpose, so that my undergrad and postgrad students will get motivated with these kind of papers and do their projects related to these topics, maybe ensemble, combining ensemble with explainable AI. So there is no other objective. It's a learning curve of my students should be improved. Thank you.